Hi, I'm Corey Cook, a scientist and product manager with Seabird Coastal. I wanted to thank you today for giving us the time to show you some applications of the cycle PO4 in situ phosphate meter. The cycle uses standard wet chemical methods for phosphate, just like an autoanalyzer in the lab would, except it's intended to be used in the water of interest or in a pumped system. Features are many, and they include these factory-prepared click-in reagent cartridges. These have a 5-month best-by date. They make it really easy to get the sensor serviced in the field and redeployed. One of these cartridges, the blue one, is an onboard traceable standard. And these reagents, before you would have to change them, you'll get about 1,500 samples, which equates to deployments that can be longer than 3 months. Where cycle does differ from the lab methods is instead of a 0.45 micron filter, we use a 7.5 micron filter. This allows it to get that 1,500 samples without the filters clogging. Cycle also has easy-to-use software, and a nice feature of that software is each data point, whether it's going to your logger or the software, has a real-time quality control flag that lets you know if the data is good, suspect, or bad. This can give you immediate confidence in your data and also let you know if you have an immediate problem. Many wet chemical systems that have failed in the past really couldn't deal with the bubbles that happen in environmental waters, so Cycle was specifically designed so it can handle high oxygen saturation, water that's changing temperature rapidly, and entrained bubbles inside the flow path. The cycle was designed to work in most environmental waters, so the ranges go to a very low limit of detection at 2.3 micrograms P per liter. It's calibrated up to 0.3 milligrams P per liter, but it has a linear range up to around 1.2 milligrams P per liter. And it can run up to 4 samples an hour. I want to talk a little bit about some applications with the cycle. Cycle is in use all around the world. It's used in the USGS, streaming live data to the internet. It's used by a lot of state agencies here in the US, and of course it's used by academic researchers all around the globe. This was an experiment we did with the consulting firm Locker Environmental and Dr. Kelly Morgan at the University of Florida. Dr. Morgan was interested in knowing how much phosphate is running off of his experimental tomato farms so that he can do best management practices research and try different methods to reduce the nutrient runoff. The Florida DEQ was really interested in what's the nutrient outflow from these drainage ditches, how much is it loading the system. We started out by building a sampling system because the drainage ditch has intermittent water levels. So we would pull water into the tanks and make measurements with the sensors inside this enclosure. Since then, the system has been advanced, it's been miniaturized, and now the cycle is actually pulling its sample, a small volume sample, from lysimeters that are buried under the rows of tomatoes. Another common application for cycle is to determine the loads. So this is in the Snake River, the point of it in Idaho, and we looked at a few different things. Typically loads here are determined by discharge or by interpolating between samples. But because the watershed hydrology is very complex, there's different regions that are agricultural or natural, depending on where the rain falls, the phosphate can change quite differently with discharge. And so this is a good example of where you can calculate load. Gives you a much finer granularity in terms of the load estimates, and also is much more accurate than using linear interpolation or, say, discharge regression. As you can see, there's times where phosphate lags discharge events and other times where events just cause dilution in the system. A quick example in the Thames River in the UK just shows cycle's accuracy. We find this time and again that grab samples line up really well with the in situ data because we're using the same chemical method that's going to be used on those samples in the lab. Cycle has really high meter-to-meter agreement. We calibrate all the sensors so that they can easily be swapped or so that they can be used at different points in a watershed to help understand transformations. So down to that detection limit of 2 micrograms P per liter, you can see changes on that level from sample to sample. And that allowed us to do experiments like this with Brian Haggard at the University of Arkansas, where he had a downstream cycle and an upstream cycle, and then a phosphorus injection point. And what he was trying to do is understand what happens in this stream reach that either takes up or releases phosphate. And here you can see in black the upstream cycle, so the higher phosphate levels, and then what typically is lower phosphate levels at the downstream cycle as phosphate is used in the stream reach or it's taken up on organic matter within the stream reach. We've had a project going in Lake Erie, western Lake Erie, from 2013 to 2015. This was a U.S. National Institute of Health project where we worked with the University of New Hampshire. We put in one of our Lobo platforms. These Lobo platforms are a buoy that has a cellular modem and then a series of sensors on it. In this case, we had the cycle phosphate sensor. We had a sensor called a water quality monitor, which does temperature, dissolved oxygen, turbidity, some fluorescence parameters. We put one of our eco fluorometers on here that measures phycocyanin fluorescence. And then this data would go publicly to the web. The site is no longer active, but for those 3 years, was serving data to the web. So what happens in western Lake Erie, as I'm sure you're familiar with, is every year they have really large microcystis blooms, and those blooms can lead to serious issues with recreation fisheries. Right, last year the city of Toledo got toxin into their water system and had to shut the water system down. So what we see here in some of the data from that Lobo in purple, we see phosphate pulses that come into the system when there's relatively low algal activity. And then after that pulse, as those nutrient levels are utilized, we start to see the phycocyanin fluorescence. More phosphate continues to come into the system throughout the summer, and the bloom just gets bigger and bigger. So you can see here after 3 phosphate pulses, this microcystin bloom is just gaining momentum and getting larger. So some of the reasons it causes this are pretty complex, and that's why we're doing this study, and of course lots of people are still studying this region. So the Maumee River definitely serves as a source for phosphate, but winds-driven events have also been shown to resuspend as much phosphate as the Maumee can deliver in, say, a year, just off the sediments on the bottom of the shallow part of western Lake Erie. I wanted to take a brief moment and talk a little bit about some of the other things we do. So besides the cyclophosphate sensor, we also have an optical nitrate sensor, so this uses no reagents. We discussed the Lobo buoy system briefly. We also make those for open ocean and for benthic systems or dock mount systems. Now, all of our instrumentation is intended for long deployments and to be able to handle high fouling environments. So as you can see here on our HydroCat multi-parameter sonde, things can get covered in barnacles or algae, and we can still make the optical measurements and still make the nutrient measurements. So we have a few different flavors of multi-parameter sondes. The HydroCat measures dissolved oxygen optically, conductivity, temperature. It also measures depth, pH, turbidity, and chlorophyll. We have standalone pH sensors, and then I also briefly mentioned a series of optical sensors that measure things like chlorophyll fluorescence, dissolved organic matter, turbidity, or can be used in dye tracing experiments. So I just wanted to thank you one more time for giving me a chance to speak today, and let you know if you have any questions to please feel free to come talk about nutrient sensors. Thanks.